solve the differential equation, which saves us a lot of effort. It says if 4 moose are introduced into this new habitat, what will the maximum number of moose in the habitat will support? 40. How do you know it's 40?
It's the limiting factor.
Because that's the limiting factor. It's sitting there. AP wants you to know that. That's why on the gateway I have that where you have to define L is the limiting factor, P is the population, K is the constant, because you need to know that information. It makes questions like this one very easy. Okay, when will the rate at which the moose population is growing be the greatest? And so, Joseph is saying when there are 20 moose. Yes. It is. Now, just for fun, let's do the work behind it. What work is there to do behind it? Take the derivative and look at the second derivative so we see when the rate is a maximum. So we have the equation for the rate of change. So I'm going to do the derivative to find when it is a maximum. So the second derivative, if you distribute, what is 0.005 times 40? 0.2 minus 0.01. Any questions so far? Set that equal to 0. And so you add the 0.1 over. Now, I know a lot of you at this point are looking for big time shortcuts, and I do like them. I do hesitate to teach it that way because what are you going to remember in May is the question. And I think you'll remember the fundamentals of calculus and how to get maximums. You may not remember those little shortcuts about it being half. Maybe you will, maybe you won't. But we want to make sure we have sound calculus to back that up in case we don't. You know what I mean by that? Or in case I say that wonderful word.
Justify.
Divide by 0.01 and we get 20 equals P. And we can even do a sign chart. And we pick a P less than 20. If our P is less than 20, 0, I get a positive. If our P is greater than 20, negative. So this P is in fact a maximum. A well-meaning but misinformed person suggests that by introducing 50 moose initially, there will be more moose available to hunt. Explain why this is faulty reasoning. The habitat can't support that much. So let's go back now. This is a different question, but it's still a logistic differential equation. So coming back to our slope field. What happens if we drop something in up here on the slope field? It goes down to that 40, right? So no matter what you introduce, you're going to head to that limiting factor of 40. In that problem, it was 30, but the same reasoning applies. So how would you explain it? Okay, the habitat can't support that many moose. If you wanted to use calculus, you would explain on a logistic slope field, being above the limiting factor, your slope is going to be negative. You could say anything to that. Yes?
Speaking with the moose, actually migrate out of the area because they're eating out of the food in the area for their studies. Maybe, I guess it depends on the day.
That's right. So I guess it depends. Okay, let's look at another one. Another very different question. So yesterday we did one where we had to do all of the hard, yucky work, and we'll do another one like that. But this one is not like that. Says a population of rabbits in a large field is given by this function. This is a logistic equation. It's not a differential equation. It's an algebra 2 equation. So it's yucky. It's a logistic equation. Determine the maximum number of rabbits this field can maintain. Now, you have a couple of options here. You tell me what are my options. E to the negative 0.7. Negative 0.7t is what that says. It is hard to read. The e is raised to the negative 0.7t. If they were asking what this is. Okay, determine the maximum number of rabbits this field can maintain. You tell me what are my options. No, okay, just knowing the formula and where the limiting factor is that one option?
It's the easiest option.
It is the easiest option. Now, sitting in May, do we remember that option or do we not? What's the other option?
Derivative.
Find the derivative, set it equal to 0, do, right? Your usual work there. So either way works great. What is the, on the formula, what is the limiting factor and where do you find it? It's the top number, right? So we know that the maximum number of rabbits, and of course, best case scenario, I hope you know that, May. But you do have calculus options if you don't. This problem is designed for us to just work with the formula and see what we can dig out from the formula. Okay, what is the value of k? So let's look at the formula. Where would we even find k in the formula?
It's e to the negative lkt.
Okay, it's e to the negative lkt. Okay, well what's L? L's 1,000, isn't it? So, negative 0.7, I think that's what that is. I don't know if it's on there or not. I'm getting it here. Is it on the calculus? Or I mean, M and L. M and L are the same. Yes. Depending on which textbook you use.
Negative. A is constant value.
Negative MK. Same as with exponential.
And A is
Also constant. Okay, so what is the value of k? I know that negative 0.7 is the negative of k, right? Or lk, depending on which formula you're using, it doesn't make any difference. And what is m? 1,000. So how will I find k? Divide by negative 1,000. What is negative 0.7 divided by negative 1,000? Don't guess.
it's 40 of 0.
What is the population when t is 0? 2.51 something like that. That is 8.16. Good question, right? But 8.163 is the population at time 0. No. What is the population when the rate of growth is the greatest? Well, when is the rate of growth the greatest? At 500, right? No, yes, rabbits. Any questions about that? Why is it 500? From the last two problems before. Because it's going to be half of the limiting factor. That's when your growth is going to be the greatest. So I want the population at when there are 500 moose, right? Is that what I want to do? Or is that what I want to do? I see no. Why not? What is the population when the rate of growth is the greatest? You said the rate of growth is the greatest when there are 500 rabbits. 500? Yeah. Why is it just 500? That is the population of rabbits, right? Then use your calculator to determine when the population reaches the value found in part B. Why would we want a calculator to do that? It's easier. We're solving that nasty exponential equation, right? 500 equals.
What's the equation?
How do you solve things in your calculator? These are both no's?
No, I got it.
You go check it close.
I did. I looked at it. I think I'm right, but okay. And actually,
Go check it. You go check it. You didn't check.
I
know you didn't because that first one's wrong.
this one put an X instead of a C. Is that gonna like?
Well, you got that wrong anyway.
Oh, I did. Okay.
Go check. Go really close. Anything that's different, you should circle it and fix it. How do you solve things using your calculator? Graph them and find the intersections. So put one side in Y1 and one side in Y2. Or you could cross multiply and do some work first. It's up to you.
The calculator lets you put in the values here.
Yeah, this is a good find a line.
Or you put Y1 in the number you want, and it gives you.
Y1 of 500?
Yeah.
That's going to give you not what you're looking for. That's going to plug 500 in for T. You don't want to do that. No. No, we don't.
I believe you can actually plug
your TI-89 will solve equations for you. You could use that as well. I don't care how you do it. You got to do it some way. I would probably use the graph, but that's up to you. If you are using the graph, what do you need to set your Y max at? Something bigger than 500, correct?
So on the last question, how did you use
the one on the slide before this?
yes, like the 80 value that you talked about?
Two slides before, or like the
moose one. So if you use the formulas that we could memorize every time, how would you find the A value?
you would have to solve with using an initial value. So you know there are 4 moose introduced to the habitat at time 0. So you would have to use that to solve.
So So you would just have to 4 in and then solve for
0 in for times 0, 4 in for the population, and you'd have to solve for A. Let's finish the problem we're on. Okay, intersection 6.857, is that what we're getting? Does anyone need me to talk about that more? Gotta get that in the calculator. Alright, I have another example for you. What's different about this one and the others? The setup of the equation is different. Does everyone agree? It does tell us it's a logistic differential equation, so theoretically we should be able to figure this out, right? So what is a logistic differential equation normally look like? Right, so we know we need a factor. I can take out a 1 over 6,000 p out. Does everyone agree? If I take a 1 over 6,000 p out, you multiply. I'm dividing out 1 over 6,000, right? So kind of like multiplying by 6,000. So what would I get if I take a 1 over 6,000 p out? What would I get on the first piece? Accurate guess?
18,000.
So now, let's ask part A again. If P of 0 is 4,000, what is the limit as T approaches infinity of P of T?
18,000.
18,000. You didn't do any work, right? How do you know it's 18,000? That is the limiting factor. Is the solution curve increasing or decreasing? And how do you know? It is increasing because you start with 4,000 fish. And I'm always going to be increasing toward that limiting factor. I'm going to level off, but I'm always going to be increasing toward that limiting factor. When would I be decreasing? If I started out above the 18,000, then I would be decreasing. That makes sense. So increasing. Justify. I don't want to just say because I'm less than my limiting factor. But since we have a value, an initial value of 4,000 being the population, this curve starts out at 4,000, right? So what is dp dt at p equals 4,000? It's greater than 0, right? What is dp dt again? Derivative, which is, what's another word for that? The slope. So since dp dt is greater than 0. Now, you can imagine if you plugged in 190,000, what would happen? You're doing way too much work. 180,000 minus, or it'd be a negative, right? Because that second piece would be negative, right? So that's when you're going to have it. If the initial population is 10,000, what's the limit as T approaches infinity. No, probably don't. Actually, if it's a good about it, if it's truly is. What about when P of 0 is 20,000? Still 18,000. I'm still going to level off to 18,000 no matter what. But my function is now decreasing because the derivative at P equals 20,000 is negative. Sketch the solution curves for parts A, B, and C. Which has an inflection point? A and aren't A and B going to be about the same? Oh, yes, because it's already past the point. You're right. So D. Now we're going to use this. This is a logistic slope field, right? They all look the same. The only difference is this thing right here, right? So right there, that thing is at 30. Ours is going to be at 18,000. And so Joseph is right. The point of inflection is going to happen when you're halfway to 18,000. So because 10,000 is above 18,000 already, you're already on that concave down part of the slope. A and what do we start out? 4,000? We'll look like that. dt squared. B, we will have already started above that point of inflection change. The 10,000s, so we're already more than halfway. So we can say yes. And I think, let me read the question again, probably. And C will be decreasing. So which has a point of inflection? A is the only one with a point of inflection. Now, let's talk about justifying a point of inflection. What would we want to use to justify a point of inflection? This second derivative. And so on the second derivative, we would say that there's no sign change. The second derivative would be, I'm going back up to the unsimplified format. It's 3p. It's easier that way. So it's 3 minus 1 over 3,000p. So A has a point of inflection because the second derivative changes signs at P equals, what did we say, 9,000? And so the other two don't have a P equals 9,000 on the graph, so we wouldn't have any sign change. Okay. Okay, I'm going to go answer Claire's question. Actually, we might could do this one. Solve for P as a function function of t? Okay, so I'm going to do this. Claire asked me, can you do this just using the formula and not using a differential equation? Yes. So you tell me if I didn't want to know, we did want to actually doing a differential equation. I want you to do your homework by doing a differential equation. You need to practice that differential equation. But the question is, if we wanted to shortcut, how would we do it? And so our function p is the limiting factor, which is what? 3,000 over 1